In this video, we're going to do a case study. And this case study is going to have a slightly different flavor than some of the other machine learning tasks that we've done so far. So our data set comes from bike share usage. So you might have seen bike shares. So you have a whole bunch of bikes that are on some kind of rack that keeps them safe. And then if you buy a membership in this bike share, or if you pay a small fee on a one-off basis, you can grab the bike and ride it around and then put it back in another docking station. So you can have the convenience and fun of biking without having to actually own a bike. So the data set for this case study was collected from the Capital Bike Share System, that's in Washington, D.C., and really nicely aggregated by the authors of the paper that I've given here, event labeling combining ensemble detectors and background knowledge from the journal Progress in Artificial Intelligence. Our aim in this case study is to use regression techniques to study some of the factors that might encourage people or discourage people from riding their bikes or from riding the system's bikes on a given day. So what we are doing here is a little bit different from the predictive machine learning that we've done before. Our primary aim is more explanatory modeling. What are the causes of the phenomena that we observe? That's going to be our main focus rather than our ability to predict unseen data. So to this end, we'll be prioritizing using a really simple model, linear regression, with very interpretable parameters. Now, I want to point out here, machine learning and statistics are very closely related, and some people would argue that these are really the same thing, but in statistics, we place an emphasis on explanatory analysis, whereas in machine learning, we place an emphasis on predictive analysis. So maybe today we're doing statistical analysis rather than machine learning. In practice, this is really quite fuzzy indeed, and people get touchy about it. So we're not going to go any further on that topic. So today what we're doing, we're using our same machine learning skills from scikit-learn, and we are using them for explanatory analysis. So I'm just going to go ahead and import our required packages, as well as what is rapidly becoming our favorite function, the retrieve data function. And I'm going to use the retrieve data function to load in our bike share data set as a familiar and comfortable pandas data frame. So this data has a lot of variables that we can play with. And fortunately, many of them are already kind of engineered in such a way as to be exceptionally useful. So we have, for example, the date as a DTE day as the column name. We have the season. So the season is a number 1 through 4, giving whether we're in spring, summer, fall, or winter. We have what year it is. There are 2 years in this data set. So the years are labeled 0 and 1. We know what month of the year it is. Each row in this data set represents a day, and then we have additional information about whether it is a holiday or whether it is, which weekday it is, whether or not it is a working day. So in this case, 1 in the working day column means that it is a weekday, and 0 means it's a weekend. We know what the weather situation is. So there are these weather codes that tell us whether it's nice and sunny or overcast or precipitating. So we have information on that. We also have normalized temperature columns and humidity columns and wind speed columns. These are normalized so that the largest possible value is 1. So there's a lot of variables that tell you about what kind of day it was and give you some of the relevant information that you might think about when determining whether or not you want to ride a bike. And then finally, we have 3 columns here that count the bicycle ridership. So these columns are casual, registered, and CNT, which stands for count, and it means total. So casual users don't buy a subscription. They actually just pay for the bike each time they rent it. Registered users pay a monthly fee and can then ride as often as they want. And then the count column is just the sum of the casual and registered users on each day. So when we think about this data set, we really could aim to predict any 3 of these columns. Today, for simplicity, I'm going to focus on the casual users. So these are the users, they might be tourists, or they might not ride bikes all that often. And we're just going to see what kinds of circumstances might encourage or discourage casual users from ponying up $1 or $2 to ride on a bicycle for a little while. So let's go ahead and check it out. we're going to start with some exploratory analysis just to get a feeling for what's going on here. It's going to be useful, first of all, since we're going to be thinking a lot about dates and times, we're going to convert the DTE day column into a proper date time column with the appropriate data type. So for that, I'm going to import the date time package. And then I'll do Bikeshare, and I'm just going to overwrite the column DTE day equals pd.toDateTime. So I have all the information I need, so I can just convert it to a date time directly. DTE day. All right, so now I have the right data type. And here already we can make a nice simple plot of the casual ridership over time. So I'll do fig x equals plt.subplots. I'm just going to make one plot, and I want it to be pretty big, so I'll do fig size equals 10 and 7. And x.plot, I'm going to plot Bikeshare DTE day on the horizontal axis and Bikeshare casual on the vertical axis. And when I do this, I get the following very large plot here. So there's a lot to take in about this plot. So first of all, really big picture, these two kind of hump shapes, they each correspond to 1 year. So that the year divides, turns over right in the middle of the plot. New Year's on January of 2012. So there does look like there might have been a slight increase in overall casual ridership from year 0 to year 1. So that's pretty interesting. On the other hand, there is a ton of variation in the data. So look, there are days that have just 200 or 300 riders, not very many at all. On the other hand, there are also days where there are more than 3,000 riders. So there's really a lot of variation. There's a really big difference day to day on whether or not you have casual riders in your system. There's this really rapid up and down movement, so that looks periodic, and maybe you might guess that the period of this oscillation is about 7 days, corresponding to weekends versus weekdays. We'll take a look at that. And then there's also some seasonal variation going on here. So we see fewer riders in winter and lots of riders in the warm summer months. So there's a lot to take in here and a lot of trends. And we're going to try for our model to capture some of them in quantitative ways. So let's take a look at that weekend versus weekday ridership question. So if I do bikeshare.groupby, and I group by working day, and then I'll just check for the average number of casual riders on a working day, I'll see a pretty clear difference. So when working day is 0, that is when we're on the weekend, there are over twice as many casual riders on average as there are on weekdays. So this is already a clear indication that we need to model the impact of whether or not it's a weekend in order to predict ridership. Now let's take a look at how this breaks down by month. So we have a couple of ways to do this. We're going to use our nice pandas group by data frame methods as well as our plotting. So I'm going to make a new summary table here, m equals bikeshare.groupby. And I'm going to group by both working day and month, which in this data set is spelled MNTH. And then I'm going to take the mean of the casual column. And when I do this, I'll just take a look at M for starters. I have the trend line by month for both weekends when working day is 0 and weekdays when working day is 1. However, this is kind of difficult to read, so let's instead make a plot instead of trying to read this table directly. So fig and ax equals plt.subplots1, and I'm going to plot. So what is m.lock0? That's the chunk of this data set that corresponds to the weekends, because that's the chunk of the data set that has index 0 in the first layer. So I'll do label equals weekends, and then we're going to do something very similar. But now I'm going to do m.lock1, label equals weekdays. So now I've plotted my 2 time series. Let's add labels. So I'll do x label equals month, and y label equals number of casual riders. And let's add a legend. Okay, so what do I have here? I have two time series over time. The blue time series tells me the average number of weekend riders in each month, and the orange time series tells me the average number of weekday riders in each month. Predictably, we can see that both of these curves, both of these time series become a lot larger in the warm summer months. So these are the months roughly 5 through 8 or so, that's May through August, and then really decrease down in December and January. Okay, so we can see that this difference where we have many, many more weekend riders does persist over time, but both of these are very strongly impacted by seasons. So that's something more that we can start looking into. Okay, question, what's the impact of weather? Does weather have anything to do with it? And if so, what? So the answer, as you might imagine, is yes. So let's do a quick analysis and take a look at the impact of weather. So I'm going to make a new summary data frame. So I'll do bikeshare.groupby. So this time I'm going to group by working day. We know that's really important. This time I'm also going to group by weather situation, weather sit, and I'm going to group by month. And then I'm going to break out by casual. I'm going to take the mean of the casual ridership. So this is a little bit too long to read, but that's okay. Okay, so next I'm going to make a new figure. This time I'm going to have 3 axes, one for each of the 3 most common weather situations. So fig and ax equals plt.subplots. 1 and 3, fig size equals 10 and 3. So this is going to be a wide figure. And I'm going to make sure that they all share the same y-axis. Okay, next, what I'm going to do is I'm going to make a dictionary of weather codes. As you might remember from that initial table, the weathers the weather column is actually just 1, 2, 3, 4, and that's not all that informative. So I looked at the README, so that's the metadata that tells me how to interpret what's in my data set. Always look at the README. So I looked at the README and I know what the codes correspond to. 1 corresponds to clear, 2 corresponds to cloudy, and 3 corresponds to light precipitation. There's also a heavy precipitation 4, but I'm not going to worry about that right now. Okay, so now for I in, let's do weather codes.keys. Okay, so for I has values 1, 2, and 3. So this gets a little bit tricky, but we can do it. So remember that the first axis is not axis 1, it's axis 0. So I need to do axi minus 1 dot plot m dot lock 0. So what does m dot lock 0 get me? That gets me the weekend trend line. But then I also need to get the trend line corresponding on weekends to that specific weather situation. So I need to do lock indexing again. So this gets me the trend line when it is clear on weekends, for example. I'm going to label that weekends. Okay, then I'm going to do the same thing, but I'm going to label this weekdays, grab the weekday trend line. So what I'm going to have here is one axis for each of my 3 weather situations. I'm going to label it using a title. So I'll do xi minus 1 dot set title equals weather codes I. And then finally, last little bit, ax0 dot legend. So let's see what we have. Okay, so we've now built up a somewhat more complicated plot where we have each of the 3 most common weather situations, and we can see that they have pretty big impacts on the casual ridership. So for example, clear and cloudy days seem to be comparable. They're not exactly the same, but they're also not wildly different. In this case, we can see that there's still a large number of casual riders in both cases. On the other hand, when there's light precipitation, the number of riders really, really drops. It looks kind of visually like it might drop by over half, actually. So the weather situation, especially whether or not there is any precipitation, seems to really matter a lot. Okay, so let's start moving toward a machine learning task. We've learned a lot about the data. We know that we need to model the months. That matters a lot. We need to model weekend versus weekday. That matters a lot. And we need to model the weather in some way. So we need to take into account these kinds of things. So we're going to take a few more variables as well. So let's go ahead and pick what they are. So I'm going to define a model DF. This is the DF that I'm going to model. Actually, let's go ahead and define the columns first. Let's do this for readability. So my columns are, I need casual. That's Y. Of course, that's my target variable. Got to have casual. I'm going to use month. I'm going to use weather sit. I'm going to use working day. So these are the variables that we know we really want, and we've already played with these. To keep things readable, let's do it vertically. Okay, I'm going to also choose what year it is because we saw that there's a small increase year over year. I'm going to choose the temperature and the humidity and the wind speed. So these are all kind of environmental variables that tell me what kind of day it is. Is it hot? Is it cold? Is it damp? Is it really windy? Those might all impact whether or not I want to ride my bike. And then finally, let's also choose holiday, because maybe whether or not it's a holiday depends. Maybe there's lots of tourists on a holiday, or maybe everyone is staying home on a holiday. We'll see whether that makes a difference as well. Okay, so model DF is then going to be equal to DF, and I'm just going to pass the calls as an index. So that's going to, oh, right, I didn't call it DF, I called it Bikeshare. Okay, so now I have a model DF containing only the variables that I want to play with. The next thing we need to do is encode the categorical month column in a way that the algorithm can understand. So there are a few different ways to do this, but in the context of linear regression, we need to do something a little bit different than what we've done before. We're going to create what are called dummy columns. So a dummy column is a 0, 1 column for each possible value of month that has a 1 if and only if the given data point has that month as its month. So what does that mean? It's a little bit awkward to describe, but let's take a look. Model DF equals PD. So now pandas actually gives us a nice function to do exactly this. PD.getDummies, kind of impolitely named, but there you go. PD.getDummies, model DF, and I need to specify what column I want to expand into dummy variables. And the column that I want to expand is the month column. And if I now check model DF, okay, so what's happened now that I've gotten the dummy variables? The month column has actually disappeared, and what's in its place are these 12 different month columns. Month 1, month 2, all the way to month 12. And each data set has a 1 value in exactly one of these columns corresponding to which month it is. So over here, these data points that have 1s in the month 1 column, those data points happened in January, for example. So now we have all these new columns that we can use for our linear regression task. We're now pretty much ready to go. So let's go ahead and separate our data into predictor and target variables. So let's do the target variables first. Y equals model DF, remember we're modeling the casual ridership, and then X equals model DF.drop. So I'm going to do everything except casual, and I need to specify the axis so that I know I'm dropping columns instead of rows. And now I am ready to go. Now, because our interest is explanatory rather than predictive, we're just going to train and evaluate the model on the same set of data for this lecture. There are potential problems with doing this, but in this particular case, I'm not too worried about overfitting. And the reason why is that we have a lot of data points, almost 800 data points for a model that doesn't have very many parameters. So overfitting, I don't think is going to be a major issue here. If your interests were predictive, of course, if you were deploying this in a business setting and you wanted to predict casual ridership, of course, you would then need to do some predictive modeling as well, but I'm not worrying about that today. Okay, so let's do our linear regression. So the first thing I need is from sklearn.linear model. Let's import linear regression. Okay, so this is the same linear regression with a mean square error loss function that we did by hand a number of lectures ago. It's just now that scikit-learn is going to do all the hard work for us. So LR equals linear regression. So I've made a linear regression model. And I'll do LR.fit x and y. And that is it for my training a machine learning model. I'm good to go. If we want, we can check the score and make sure that our model is actually measuring something. So let's check. We'll do lr.score. And we see that the score in this case, so the score is measured by the coefficient of variation for linear models. And in this case, the score is about 73%. Is that good? Is that bad? Well, we'd have to do some more checking on that. And of course, we would want to check to guard against overfitting as well. But for now, what I want to actually do is just visualize how our model did at replicating the actual data. So I want to visualize the trend line that actually happened in comparison to the trend line that the model thinks should happen. So this is actually lovely and easy to create. All we need to do is add a Preds column to the original Bikeshare data. So we'll do Bikeshare Preds. And we get this by doing lr.predict on x. So lr.predict on x, that's just the result of asking the model, what do you think the value should be on each of these predicting data points? And then we add that as a new column to the original data, Bikeshare Preds. Let's visualize. So fig and x equals plt.subplots. 1 and fig size equals 10 and 7. Nice big figure again. First, I'll plot the original data. So x.plot Bikeshare DTE day against Bikeshare casual. And this is the observed data. And then next, I'm going to plot Bikeshare DTE day against Bikeshare Preds, and this is the modeled, not data, it's the model predictions, and we'll do x.legend to distinguish them. So let's take a look. So what do we have here? We have the modeled outcomes of our pretty simple linear model in orange. And we can see that our model has succeeded in certain ways and maybe not succeeded in others. So what are some ways that it has succeeded? Well, we do have this really strong up and down oscillation corresponding to weekends versus weekdays. Although it sort of looks visually like the model may actually not have captured the full extent of this oscillation. It looks like there's actually a much stronger oscillation, for example, in year 2 in the summer months. It looks like we have captured seasonal variation. The model gives smaller modeled values in the winter and larger ones in the summer, so that's pretty good. There are some weirdnesses here. So for example, if you look at the very beginning, down near January of 2011, so that's the bottom left corner, our model is actually giving some negative values. Okay, so you can't have negative ridership on your Bikeshare system. That doesn't make any sense. So we can see that there are some ways in which our model has really not succeeded as well, and improving on this and developing something that fits the data even better would be an important ongoing task. So overall, qualified success. We have done some things well and other things are in need of improvement. Okay, so considering how simple this was to put together, it's a pretty good start actually, and we can really work on using different models or incorporating the data in different ways to achieve better outputs. Now, recall that our main aim was actually to learn something about what conditions make for lots of ridership. So like, when do people want to ride their bikes? What kind of days are those? And linear models are really good for this because we can actually just investigate the coefficients and see what the coefficients say about the impact of different variables on the ridership. So that's why one of the reasons linear models are so great is that they're so interpretable. So I'm going to display these as a data frame. So I'll construct a dictionary. So x.columns gives me the column names of x, and then coef, so let's just actually just call it coefficient, nice and explicit. So coef here, we get the linear model coefficients by taking the model itself, and we access the coef attribute. And then I just want to round it to 2 decimal places just for readability. And I'm going to display this all as a data frame to make it nice to look at. So when we do this, we can start seeing what kinds of variables make a difference in our model. So let's start at the beginning. Larger values of weather sit corresponded to more precipitation. And we can see that that's reflected here. When we have more precipitation, the coefficient is negative. So that means more precipitation, fewer riders. The coefficient of working day is very strongly negative, -800. So that indicates after controlling for the other variables, we have over 800 fewer riders on weekdays than on weekends. There's a positive coefficient for year, reflecting the fact that when year goes from 0 to 1, we see more riders on average. Warmer days, so warmer temperatures lead to many, many more riders. Humid days and days with lots of wind are less attractive. You'll see fewer riders on those days. Holidays turn out to have relatively few riders. This needs to be carefully interpreted in the context of like holidays being correlated with months, but we are not going to worry about that now. And then, of course, you can also see the impact of seasonality on ridership. So, for example, months 1 and 2, that's January and February. Months 11 and 12, November, December, those have negative coefficients. You're going to see not all that many riders on those months. On the other hand, you will see more riders in the warmer months, like 4 through 8 or so, or 9. So you'll start seeing more riders that way. So our model is nicely capturing some of the features that we saw in our monthly variation as well. Okay, so this was a long video. We did a kind of extended case study where we went through some exploratory analysis and some modeling in order to learn something about our data set. So you have to be really careful in interpreting these coefficients, and a lot more work would need to be done here. But we can start seeing how different layers of visualization and modeling can start building our understanding of real phenomena that can matter for science and business decisions. So as usual, we are not done with this analysis, and the next things we would do would be to keep asking questions, keep expanding on our methods, and keep building our understanding as we model, transform, and visualize, and ultimately communicate our results. That's all for this case study. Thank you very much for joining me today.